welcome back. This is lecture 30. In the previous lecture, we were discussing differential amplifier, right? So let's continue our discussion on the same topic. So this was the structure that we were interested in. Right, and we also saw that the current that comes out of this structure, right? So if we apply so the incremental equivalent of this structure is essentially this, where the Vx terminal is open in its incremental sense. So this current becomes Gm V1 minus Vx, and the other current becomes Gm, so Gm1, this is Gm2, V2 minus Vx, and this goes into the load resistance Rd, right? So this was essentially the incremental equivalent of our structure, and we are getting the output from this node, right? And what did we see? We saw that this is nothing but this, the current, the incremental current that is flowing into the resistance Rd was how much? The incremental current that was flowing in after we did KCL, KVL and all those applications and everything was proportional to some proportionally constant Gm times V1 minus V2, where Gm was Gm1 Gm2 by Gm1 plus Gm2, right? Okay, and what was Vx? Vx was also essentially weighted average of the voltages, incremental voltages at V1 and V2, right? So basically Gm1 V1 plus Gm2 V2 by Gm1 plus Gm2. This is what we observed, right? So so as it turns out, this differential amplifier structure is a very ubiquitous structure, and it is used everywhere. And instead of using this entire symbol each time, what we generally tend to do is reduce the footprint of the symbol and express it in a much compact form. So what I mean by that is, what is a common source amplifier? A common source amplifier is a case where I have an input, let's say I call it V1, right? So this current is Gm times V1, and this is flowing out. I am ignoring channel length modulation. So your common source amplifier essentially becomes this. The stuff inside the box is a common source amplifier. Why? Because the current that is coming in is Gm times V1, where V1 is a voltage between some reference and which is connected to the source and the gate voltage, right? So in case of if we have to black box our differential amplifier, so what should that black box look like? So in case of if I black box the differential amplifier, and instead of sketching this entire differential amplifier topology, what should it look like? It would look like as if there is a current of some Gm times V1 minus V2 that is flowing out when there is a input V1 and V2, correct? And where is this current flowing out? This current is essentially flowing out of some internal reference, right? What is the difference between this structure and the common source amplifier? The structure that is the difference is that reference point in case of a common source amplifier was a source terminal, and the voltage at the input side was being also referred to that source terminal. However, in our case, in a differential amplifier, the output current is still the difference between two terminals. Like in case of a common source amplifier, the output current was a difference between the gate terminal and the source terminal. In our differential amplifier case, the output current is again difference of two terminals, that is V1 and V2, but note that neither V1 or V2 are source terminals, right? So that is a critical difference. Other than that, as far as the current output is concerned, this is exactly similar to a common source amplifier. Okay, so in other words, okay, so if I have to make it more explicit, I should maybe say it in this way. If this is Vs and this is V1, so this current is Gm V1 minus Vs. This is Gm V1 minus Vs, right? Note that this current Gm V1 minus Vs is flowing into the source. In our case, in a differential amplifier, the output current is again still proportional to V1 and V2, right? Just like in case of our common source amplifier, the current is proportional between V1 and Vs. However, this current is not flowing into the source. The current is flowing into some internal reference. Okay, that is why this structure is again shortened and expressed in this format. And we simply call this Gm, where it is assumed this structure that you see here, right? This almost like a triangle whose nose has been chopped off, right? It's almost like a triangle whose nose has been chopped off. So this is a voltage controlled current source whose proportionally constant is Gm. So whenever we have this structure, this means that I am referring to this structure, right? Which means the current that is coming out is Gm times V1 minus V2. Okay. Okay, so going forward in another lecture or so, you will see that we will not be, whenever we are trying to deal with differential amplifiers in a broader sense, right? When we have to deal with multiple amplifiers put together, then we will see that will not represent that differential amplifier with multiple voltage control current sources. We will essentially combine all of them, right? We will combine these multiple voltage control current sources that a differential amplifier is that is used to make a differential amplifier, and put it and represent them as a symbol, and the symbol is something that I just showed here. All you have to be mindful about is this input impedance from either of these terminals are infinity, right? So here it's open circuit, no current flows in. Also, the other thing that you need to note is what is the output impedance? Output impedance is also infinity because it's a voltage control current source. Okay, fine. So let's get back to what we were discussing. So let's assume to start off that since the structure, as from the perspective of the transistors and the way we are feeding the input, seems symmetric, let's assume that both of these have same W by L. they did not have the same W by L, but let's assume that they have to start off. Okay, and also let's assume that we are only bothered with quiescent condition right now, and let's again further assume that this voltage is VB1, this voltage is VB2, right? Okay. So if you recall, when we stopped when we ended the previous lecture, we were in the midst of representing inputs as sum of common mode and differential inputs, right? So why is this relevant? This is relevant because I can say that VB1 is equal to sum VB1 plus VB2 over 2 plus VB1 minus VB2 over 2, right? And VB2 to be equal to right. Okay, so let's say VB1 plus VB2 over 2 to be a common mode, right? Let's call this VCM and let's call this delta VB, right? So if that is the case, what do I see? I can represent these inputs as VCM connected at both nodes, both inputs, and another signal which is delta VB here, and delta VB minus delta VB at the other terminal. Correct? So why am I doing all these things? I'm doing all these things because if delta VB is small, right, if it falls within that range of small signal, whatever we call it as small signal, if that is true, then I can express that. So if delta VB is within quotes small, then it can be expressed as a differential input on top of common mode VCM. Correct? Okay. So so why are we saying this? We are doing all these things because ultimately we love symmetry, right? If we have symmetry, then circuit analysis becomes easier, right? So that's why we would like to break it up in such a way that we'd like to arrange the inputs for our analysis in such a way that a symmetry is established. Okay. So if this were the case, under quiescent condition, right? Under quiescent condition, what do we mean by quiescent condition? Under this, the quiescent condition seems to be that when delta VB were not there and we only had VCM, right? If we only had VCM, what can you comment on the current? Let's say I call this I1 and I call this I2. What will be current I1 and I2? So I1 will be half mu n Cox W over L VCM minus Vx minus threshold voltage whole squared. What will be I2? This will also be half mu n Cox W over L VCM minus Vx minus threshold voltage whole squared. So essentially, what is the scenario? I1 is equal to I2, and since I1 plus I2 is I0, so this becomes I0 over 2, right? So under quiescent condition, both the quiescent currents through both the transistors M1 and M2 are identical, right? So this current is I naught over 2, and this current is also I naught over 2, correct? So why am I bothered with this? I'm bothered with this because now if we introduce this plus minus delta V, delta VB, and minus delta VB, what can we say? We can say that application of plus delta VB and minus delta VB will create a incremental current, right? And how much that incremental current will be? This will be equal to GM times V1 minus V2. What is V1 in this case? V1 is plus delta VB, and what is V2? It's minus delta VB, right? So in essence, on top of the quiescent currents, GM times 2 delta VB, right? So what will be the current? What will be the total current through M1? So total current through M1 will be I naught by 2 plus GM delta VB, and total current through M2 will be I naught 2 minus GM times delta VB. Why minus? Because note that the incremental current is flowing in the opposite direction to that of I naught by 2, right? So essentially that current is decreasing, right? Another way of thinking about it is, when you are applying plus delta VB at the gate of M1 and minus delta VB at the gate of M2, what is happening to the overdrive of M1? You are increasing the overdrive of M1 and you are decreasing the overdrive of M2. Now note that the current of I naught earlier was splitting equally between both M1 and M2 because they had identical overdrives. Now that you have more overdrive on M1 and less overdrive in M2, then more current will tend to gravitate towards M1 and less to M2. And how much will be that more and small be? If we can apply small signal approximation, then that will be GM times delta VB. Okay, and what is GM? GM was GM1 GM2 by GM1 plus GM2. But what is GM1 and GM2 now? GM1 and GM2 are quiescent transconductance of M1 and M2 evaluated under what condition? Evaluated on the under the condition that both of them have currents of I naught by 2. So GM1, what is GM1? GM1 is under root 2 mu n C ox W over L I naught by 2, which is exactly equal to GM2, and let's call this GM. So effectively this GM becomes GM of 2, GM by 2, right? GM1 by 2. Okay, right? Okay, so it seems like the incremental current, right? So if I have to represent this again as in the symbolic form that we just derived, what are we seeing? We are seeing incrementally, if we have an input delta VB here minus delta VB here, the current that is flowing out is GM1 by 2 times 2 delta VB, which is equal to GM1 times delta VB. Okay. Okay. So, fine. So, what is the moral of the story? The moral of the story is, there are several models. The primary one that we are discussing in this case was, if we don't have identical bias conditions at the inputs at the gates of M1 and M2, and assuming that the biases are slightly off, right? By slightly off, I mean the delta VB is difference between the bias can be attributed, can be thought of as small signal difference. Then we can as well say that both the transistors are biased identically with a common mode voltage, which is average of the biases, and we understand that because the biases are different, there will be a difference current. The current will not be identical between the two branches, but the difference current can be approximated as a small signal difference, which is equivalent to the transconductance, the equivalent transconductance of the differential amplifier, which is GM1 GM2 by GM1 plus GM2, which is equal to GM1 by 2 in this case, and times the voltage difference of the two inputs, right? So since we have this way of since we have a mechanism of dealing with difference voltages, even if the difference is in the bias, right? So what we will do going forward is assume that both the transistors are biased with identical bias voltages, right? And whatever input we might be applying at their gates, or the difference in input can be because of difference in bias voltages, or for some difference, some input difference accrued, we will relegate all of them to say to as if they are part of some input. Okay, fine. So in essence, what we are essentially doing is this: the structure that we'll be dealing with from now on is same bias. Let's call this VCM, and we'll have some input V1, and let's call this VCM also, and we'll have some input V2. Okay, fine. Now what about the sizes of M1 and M2, right? We didn't assume that sizes of M1 and kind of sneakily assume that both the sizes are identical, but they also need not be identical, right? I mean, free country, you can decide to choose W by L of M1 and M2 to be different. Yes, indeed you can. So if that is the case, what's going to happen? Intuitively, what do you think is going to happen? If W by L1 is more than W by L2, if W by L1 is more than W by L2, then M1 is stronger than M2. Correct? Note that the VGS of both M1 and M2 are identical, right? So VGS of M1 is equal to VGS of M2. Why? Because both their gates are quiescent wise, both their gates are at same voltages, their sources are tied together, and the threshold voltage are also same, which means they have same overdrive also, which means V overdrive of M1 is equal to V overdrive of M2. Correct? So if the W by L of M1 is more than W by L of L2, correct? So then if W by L1 is greater than W by L of M2, then what's going to happen? The I1, right? The current I1 will be greater than I2. And what is sacrosanct? The sacrosanct condition is I1 plus I2 is always equal to I0. Correct? So you can write out the equations. You can write out the saturation condition equations of M1 and M2, and you will be able to find out what will be the exact I1 and what will be the exact I2. Once you know what the exact I1s and I2s are, then you will know what the transconductance are, what is GM1 and GM2. Moment you know what the transconductances are, then you can effectively use the structure and say that in order to establish what is a small signal equivalent, I can essentially represent this guy as V1, V2, GM, where GM is GM1, GM2 by GM1 plus GM2. The current that is flowing out, right? Current that is flowing out is GM times V1 minus V2. Where now note that GM is not identical. I mean, GM1 is not equal to GM2, right? So in this case, I have to say that. Then GM becomes GM1, GM2 by GM1 plus GM2. Correct? And where is this incremental current flowing? This incremental, I mean, all we have done is show you the incremental structure of this guy. right, without the RD, correct? We have been only dealing with the incremental structure of the voltage control current source without the RD. Where is this guy flowing? This current is flowing, this is flowing into RD. And what voltage it will generate here? The voltage that it will generate is Gm times V1 minus V2 times RD, correct? So, which essentially means that what is the gain? What is the differential gain? Differential gain is Gm times V1, so what is V0? V0 is Gm times V1 minus V2 times RD, or differential gain is V0 over V1 minus V2, which is Gm times RD, right? Okay, fine. So another way of representing the same structure is to Nortonize, is to sketch a Norton equivalent of the same. And if we have to sketch a Norton equivalent of a structure, what will we see? Let's do one from scratch. I'm not showing the biasing now. Let's assume we have the biasing there, but I'm not showing it explicitly. If this is V0, right? So if we have to do the Norton equivalent, what should we do? We should short it, right? Now note that this short is an incremental short, right? Not an absolute short. If this is an incremental short, how much current will flow into that incremental short? The incremental current that is flowing out is Gm times V1 minus V2. And where will this current go? This current will go into this node, and it will only go into the short, right? Because it need not go into RD, because it's seeing a zero impedance in the short. So this short circuit current ISC will be Gm times V1 minus V2. Great. So this becomes ISC. What is the output impedance? What is the output impedance? How do I know what is the output impedance? So this is shorted, this is RD. This is shorted also because while doing output impedances, we don't consider, we have to desensitize the input. Desensitizing a voltage source is equivalent to shorting the voltage source. And we can remove this current source also, because in an incremental sense, current source is irrelevant. This is Vx. And we apply a test voltage here. And we have to find out what this test current, right? This test current here. Okay, so let's do it in two ways. In one way, let's neglect the channel length modulation, right? If we neglect the channel length modulation, what do you think will be the current that is flowing in? So if we neglect channel length modulation, what is the RDS? What is the RDS of this device? This RDS is infinite, which means this is out of picture. What do you think is happening with gates? The gates are shorted, right? The gates are shorted to ground, right? Which means that there cannot be any current, right? Because there is no way the source voltage can be excited, because nothing can flow from top to bottom, right? So this is equivalent to saying that no current flows here, so this guy doesn't exist, right? Then what is the where will the test current go? The test current can only go upstairs into RD. So what is R out then? R out is equal to, right? So what is the Norton equivalent of a structure? The Norton equivalent of a structure becomes a current source. The short circuit current is a current source, and the output resistance is RD, this current source value is GM times V1 minus V2. Correct? Note the direction of the current, right? The direction of the current is flowing out, right? Flowing into the load because the direction of the current is as shown here. Okay, so this is different from a common source amplifier where the direction of the current is flowing out of the load. Okay. So next, let's consider what's going to be the output resistance in presence of channel length modulation, right? So let's do that. So again, we would like to, and we'll assume that the biases are set, right? So we will not be showing the biases explicitly. So this goes ground, this also goes to ground. This is Vx. We apply a test voltage, and we have to figure out what is the effective resistance, right? So let's do it in two parts. So this is also grounded, right? Okay, so let's do it in two parts. So first part, let's say that we like to find out what is the current going down and what is the current going up. What is the current going up is easy. What is the current going up? The current going into RD is V test over RD. So no problem with that. We need to establish what is the current flowing downwards. So how should we establish that? So we'll have to then put back the resistances, correct? So let's call this RDS1. Let me take some extra space because otherwise I'll not have place to accommodate all the components. So let's call this RDS1. We'll have here RDS2. This is shorted, right? So we don't need this, and this is also shorted. Okay, fine. So this, if we have to find out what is the impedance looking down, this seems to be a complicated structure. So moment something becomes slightly complicated, what we would like to do is break it down into smaller structures. That is the principle of engineering anyways. So you break things down into smaller structures and try to make sense of it. So when I say that, what do I essentially mean? What I essentially mean is this. So if I only look at this structure, right? If I only look at this structure, what should I see? I should see this. Should see by the way, note that okay, I think I have sketched the RDS1, RDS2 the other direction. This should be RDS1, this should be RDS2, right? So this is RDS1. Okay, sorry, this is RDS2 because we are applying test voltage here, right? Note that what we are assuming is when I sketch a transistor and place RDS here, what I am essentially assuming is the structure is equivalent to this, right? So I don't want to replace the transistor with its incremental equivalent all the time. So I am superimposing the incremental output resistances on top of the transistor, and we assume that the transistor represents a ideal voltage control current source, right? So that's the inherent assumption. Okay, fine. That is something that we need to understand before we proceed. Okay, fine. So this, if this is M2, right? So what is this node? This node becomes Vx. And what is connected to Vx? What is connected to Vx? We have M1 whose gate is grounded, right? Whose M1 whose gate is grounded and the drain is shorted, correct? And M1 also has its output resistance RDS1. Okay, okay, fine. So what are we looking for? We are looking for the output resistance looking down, right? We are looking for the output resistance here, right? So again, this seems to be a complicated structure. So let's simplify it further. So how should we simplify it? So in order to simplify it, we first need to take a break, pause for a moment, and try to answer this question: that is there a particular structure that we are comfortable with from the knowledge, from whatever we have done in this course, right? So can you recall a structure which has in which something is connected to the source of the transistor, and we need to find out the output resistance of that structure looking into the drain of the transistor? Have we done that? So what I'm essentially saying is this: have we found out the output resistance of this contraption before? Looking into the drain, let's say this is some R0. We have, right? We have, when we were doing cascode current mirrors, right? When we were doing right, cascode configurations, we found out what is output resistance. And what was output resistance? This R out was GM times RDS times R0 plus RDS plus R0. Correct? So do you see a resemblance of this structure with this structure? There seems to be some resemblance, because at least we have the structure here which is equivalent to this structure, but we have something connected at the source of the transistor instead of R0. So if we can find out what is this equivalent R0, right, in terms of the parameters of M1, then we are all set. So essentially what is the next question that we are asking? The next question that we are asking is, what is the impedance looking into this terminal of M1? So right, what is the looking in impedance into that terminal of M1? Have we done that before? Yes, we have, because have we done this structure before? This is grounded, this is grounded. What is the looking in impedance here? We have done this before. What is that? That is equal to 1 over GM plus GDS. Correct? This is almost equal to 1 over GM, as long as the GM is much more than GDS, right? So which essentially means that what does this structure reduce to? The structure reduces to the following structure. So we have something connected here. What is connected here? 1 over GM1, and this is RDS2, and we are trying to find out what is the impedance looking here, right? What is R out? Then what is R out? If you simply plug this in this formulae, what should I get? I should get clearly the summation of two R's, RDS2 plus 1 over GM1 plus, what is the important thing? What is the extra stuff? The extra stuff is GM of this guy, GM of M2, right, times RDS of M2, right, intrinsic gain of the transistor, times the load, right? What is the load? 1 over GM1. Correct? So if GM1 is equal to GM2, if the bias, if W by L's are same, right? If GM1 is equal to GM2, then R out becomes RDS plus 1 over GM plus RDS. Again, RDS will be same, because if GM1 equal to GM2, then RDS1 also is likely to be equal to RDS2, because same current, same size, so same RDS, which is approximately equal to RDS, right? So this is approximately equal to RDS, right? Okay, so what does the Norton equivalent of our structure reduce to? Now the Norton equivalent of our structure becomes some GM times V1 minus V2 to RDS and RD in parallel. Because why this RD is in parallel? Because note that now the resistance looking down, becomes R down, let's say, becomes 2 RDS. What is R up? R up becomes RD. So these two are in parallel. So essentially we get this structure. This becomes the Norton equivalent of our differential amplifier. Okay. Now you might turn around and say that I have cheated, because while trying to find out the incremental resistances, I use channel length modulation, all good. But while trying to find out the transconductance, the equivalent transconductance, I have till now neglected channel length modulation, right? So what happens if I don't neglect channel length modulation while trying to figure out what is the transconductance? So this is going to we can do that also. So I would like to assure you that I have not cheated, but I have made some approximations, right? So what is the approximation? Let's see. So since we are shorting the output, I did not bother with the RD, because these are anyways getting shorted. Okay. So let's call this RDS. Let's call this RDS. Okay. Okay. So how should we go about figuring this out? We can go about figuring this out in one of two ways. Let's do the generic ways first, right? What is the generic way? The generic way is use superposition, right? So let's use superposition. If we use superposition, what's going to happen? We'll use V1 once and V2 ground. While grounding V2, then we'll apply V2 and then ground V1, right? So use superposition. What should we get? What do you think will happen? Let's use the same funda. So what is the impedance looking in here? This is 1 over GM plus GDS, which is again approximately 1 over GM, correct? And then what is the current that is flowing in? What is the current that is flowing in here? What is this current that will be flowing out, right? This is ISC. This current that will be flowing out will be this current, right? Will be equal to ISC, because if I consider this to be a box, whatever goes inside the box has to come outside the box from the other terminal, because nowhere else it can go, right? Whatever comes into this circle has to go out from the other circle. It's like a pipe, right? Whatever comes in has to go out from the other side, because it cannot leak anywhere else. There is no path to leak, right? So if the short circuit current is ISC, let me call this ISC1, right? ISC1, then the current at the input of the at the source terminal of the transistor will also be ISC1. Essentially, what the question that we are asking is, what is this? If this is 1 by GM, what is this current? This current is ISC1, right? This is V1, this is grounded. What is this current? Note that this structure is also something that we have done before, right? Remember a voltage controlled current source which was loaded with a resistance. Remember that? Remember the topology of common drain amplifier? What was the incremental current when the common drain amplifier was trying to drive a load? The incremental current was, I mean, if let's say this is equal to some RL, so what would have been the incremental current? In this case, ISC1 was GM1 by GM1 V1 by, this is again approximation, GM1 V1 by 1 plus GM1 RL, correct? So this was GM2, right? This is GM2. So this is equal to, in this case, equal to GM1 V1 by 2, because GM1 is equal to GM2 and RL is 1 by GM2. So this becomes ISC1 becomes GM1 by 2 times V1, correct? Now let's put back V2, let's put back V2 and short V1. So then what should we get? Short V1, put back V2, and let's try to find out what will be the ISC1, ISC2, correct? Okay, so same old, what is it? So what is the impedance now looking this side? This is 1 by GM1, right? If that is the impedance looking that 1 by GM1, what is the current? What is this current? This current will be, this is GM1, this is GM2. So this current will be GM2 by GM2 V2 by 1 plus GM2 by GM1 times 1 plus by GM2 by GM1, right? RL is GM1. So this is equal to GM1 V2 by 2, because GM1 equal to GM2, correct? So what is ISC1? ISC2? Then ISC2 becomes minus GM1 V2 by 2, correct? So what is the total ISC? Is the superposition of two ISCs. So ISC becomes ISC1 plus ISC2, which becomes GM1 minus V1 minus V2 by 2, right? So see, I mean, essentially channel length modulation doesn't really affect the transconductance to a significant amount, right? So if we take intelligent approximations, we can get away without taking the full-blown models, right? Essentially that's what the takeaway is. Also note that you must have also already seen that we have used, while trying to analyze these circuits, we have used a lot of our past knowledge, right? We have used the formulae that we have used before, right? What did we do? We broke the circuit up into multiple small fractions, multiple small parts, so that we can break it down into elements such that into not any old elements, into elements that are known to us, right? So we have covered those elements, we have covered those structures at the beginning of the course, at the first half of the course, right? So we are using those existing knowledge to analyze these circuits, right? So my sincere request will be, if you find this type of analysis slightly tricky, then go back a few lectures and refamiliarize yourself with the structures of common gate amplifier, common drain amplifier, right? And what will be the input impedance, what will be the short circuit current, what will be the output impedance. Refamiliarize yourself with these structures, so that using these topologies, such that analysis of these topologies using those structures will be will become easier, right? Because going forward, you will see that we will be using abstractions of these structures repeatedly, right? If we have like 10 transistors in a network, it's physically not possible to put small signal equivalents of all of them together and do an analysis. I mean, it's possible definitely, but it will take you hours. A simulator can do that job much faster than we human beings can. However, even if you can do that, it will not give us any insight. So in order to get an insight, what we would like to do is to black box items into smaller and smaller sections, so that we understand what those sections are and use those elements as is. This is equivalent to the example that you can think of. This is equivalent to learning tables, right? When we were in school, we told that you learn the tables of 4, 5, 6, 7, 8, 9 and all those things, right? So one might turn around and say, we know that a table is repeated addition, right? So if I tell you if I ask you what is 7 times 8, I can say that 7 times 8 is 7 plus 7 plus 7 plus 7 and go on to 8 times, and I'll get an answer and it will be correct. But it will be super inefficient, right? Because if I know the multiplication table of 7, then I know 7 times 8 is 56, right? So if you compare yourself with somebody who knows the table and with somebody who knows the principle behind it and spends the entire time figuring out what 7 times 8 is, then you can readily guess who will be able to go further, right, using that information, right? So now that we have graduated from the single transistor circuits of common source amplifier, common drain amplifier, common gate amplifier, right? So I would request you to refamiliarize yourself with the structures of with at least the rudimentary behaviors and the rudimentary output impedance, short circuit currents, or the Norton equivalents of those structures, so that we can pull them and use them for our advantages going forward, right? Okay.